So our next speakers are Philip James and Asheesh Laroia. Philip comes to us from Patreon, where he is leading platform engineering and is also an organizer for DjangoCon. And Asheesh is currently a software engineer at large and has worked with several other Python organizations whose names have fallen out of my head, unfortunately. They're going to talk to us about security and side channel attacks. Please make them feel very welcome as I turn the microphones on.
All right.
Hello.
Hello.
Can everyone hear me? Great.
I can hear you.
Fantastic.
Good.
Hi there. I'm Philip James.
I'm Asheesh Laroia.
Let's try that timing again.
Okay.
Hi there. I'm Philip James. This is my friend Asheesh Laroia. This talk is all in the timing, so if you're walking in a little late or have to leave a little early, that's okay, but you might not get the full experience because it's all in the timing. This talk is called All in the Timing because we're going to be talking about a category of attacks against computer systems called timing attacks. Like I said, I'm Philip James.
I'm Asheesh Laroia.
And we got the timing. This talk is called All in the Timing, but we're talking about side channel attacks, like I said. Previously, if you've been to other Python conferences, you may have seen us give talks such as type Python, press enter, what happens, or type uwizgi, press enter, what happens. We could not come up with a type blank, press enter, what happens title for this talk, but we have a trend of giving talks about system-level concepts that we describe through Python, and this talk is going to be no different. Asheesh is going to tell you about what our goals are for today.
Yes, thanks, Philip. So there are 3 goals for today's presentation. I want to first explain timing attacks in general so that you can see them when you're reading code. Second, I want to show you a real-world example of a timing attack in some Python code and what it took to fix that issue. And finally, I want to show you some examples of side channel attacks in general. We'll show you 2 side channel attacks that realistically affected Python web applications. And we'll also go into a now infamous attack against Intel CPUs. And our goal will be to teach you enough computer architecture in the last 5 minutes of this presentation so you can understand the Meltdown bug. We'll see if that works. The point of the talk as a whole is to give you more concepts, help you see opportunities for security, issues you can fix in your own code, and understand how to avoid those issues in the first place. You might be introducing timing attack opportunities into your own code, and it's fun to see that when you can through this talk, hopefully. And you'll be able to do something to prevent those from happening. So that's a bit of intro. Who wants to see some broken web applications? Wow, all right, we've got an audience today. OK, so here is a login form that Philip designed. Actually, it looks really nice. And on this form, somebody can submit a username and a password. And the system behind the form will give you a yes or no answer as to whether or not that combination was correct. How many of you have used a form like this? I'm really glad this audience is awake. This is really good. If I weren't giving this talk, I'd be much more tired right now after lunch. So if you think about this login form as letting you try passwords one at a time, there is a way to find out the right password if you know somebody's username, and that's guessing every possible password. That's also known as brute force. I'll show the math for how many possible passwords there are now. Let's say our password length is 8 characters long. And let's say for each possible character in the password, there are 36 possible characters, the letters A through Z, the numbers 0 through 9. These are close to the worst password rules you could come up with, but they make for a good example. So the total number of combinations here possible is 36 to the 8th power, which is about 3 trillion. If you could try one password after another in sequence, and it takes 1 millisecond to check each one on that login form, then it would take almost 100 years to try every possible password. That means that if I'm personally the attacker, I won't be alive when the attack finishes. If I'm the person running the system, that's pretty good. But sadly, the password checking for this form makes password guessing even easier than it should be. So for this form, it takes different amounts of time to guess the password. Sorry, it takes the back end different amounts of time to check the password based on how correct your guess is. And so I'm indicating that with a little timing logo here. This will happen because this form uses Python's double equals operator in the back end to compare the password you present against the password that is stored. This isn't Python's fault. This would be mine as the system developer. But to understand why it works this way, we need to understand the double equals operator. So I'm going to show you how Python double equals compares a few different strings. You'll see that it finishes faster based on how similar the strings are when compared left to right. So we'll compare password against massword first. The Python interpreter checks the first letter and concludes that there's a mismatch, and it can return false. If you're checking against a string that has a bunch of letters in sequence that are similar, we'll see how that looks now. Pass 1, 2, 3, the comparison has to look at the first letter. That works. The second letter. That works. And so on, until it finally gets to a mismatch. And so you've seen it did about 5 operations here, whereas the first time it only had to do 1. Finally, if we check password against password with the Python equals equals operator, the Python interpreter has to check each character one at a time, doing 8 operations until it finally concludes that, yes, these are the same. So we can guess the whole string if we have that going for us in 144 tries. And here's how. We know that equals equals gets slower the more characters you have right, going left to right. And so instead of having to guess each possible password, we can focus on guessing just the first letter. On average, well, the first letter, on average, will take about 18 tries, 36 divided by 2. So the system tells us through timing if the first letter is right, and then we can go check the next one. That adds up to 144 tries, because it's 18 times the number of letters. And if that takes us 1 millisecond per try, just like before, that's 144 milliseconds. That's a lot faster than 90 years. So if we get academic about this, this is a linear number of guesses versus exponential number of guesses. In this graph, the top line is exponential, the bottom line is linear. The x-axis here is the number of characters in the password, and the y-axis is the number of guesses required to guess the right password. We want password guessing to take an exponential number of guesses. But because of how this form implemented it, it's linear. Timing attacks are interesting not just because of how they work, but because they let you do something that should take exponential time in linear time. Next up, Philip will show you what happens when you measure that using Python's double equals operator.
So let's see the timing in action. I'll start by measuring the runtime of some functions that might be used for a previous password example. Here, I'm using the IPython profiling function called timeIt to show that plain string comparisons in Python have different times for different strings. Now, as a side note, I'm doing the .encode dance here because when you do string comparisons of 2 different things in Python, if they are literally the same string, it assumes it is the same object and returns instantly, which doesn't make for a very good example. If you were taking this input from a user, they would not be literally the same thing, and so you would see the timings like we're seeing here. These timings are still pretty fast, but if you look, we're getting measurable difference in how long a function takes to run based on how many letters we got right in our guess, a spread of around 20 seconds, which is pretty wild. We call this data-dependent time because the input data changes how long something takes to run. The standard advice people give you when you ask about timing attacks is make everything take the same amount of time. This is called a constant time operation. It's called constant time because it doesn't change how long it takes based on input that your attacker controls. Here's a similar timeIt profile for string comparisons using Django's constant time compare function, which is the function that Django uses to compare password hashes. It really is constant time plus or minus some small system noise. Now, as another side note, computers are rocks that we tricked into thinking by shoving lightning into them, and we keep finding new ways to shove lightning into the rocks. And we want to shove the most efficient amount of lightning into the rocks. And so if you try this on your computer when it's not plugged in, your computer may not return these constant timings because your computer is doing micro-optimizations to conserve battery power when it's not connected to power. And you'll see different timings even on constant time compare. Don't run your servers on battery power. Computer scientists like to call this big O of 1, so you can do that too, I guess. To drive this home, let's talk about a real Python code base that had to fix a timing attack. The attack is a little different than the password example, but the principles are the same. The big picture is that thanks to a timing flaw, you could get a signature verification library, a library that was supposed to prove whether a signature was correct, and use that library to generate a valid signature for you. Let's talk about how that happened. The library we're going to talk about is a library published by Google called Keysar. It has a bunch of cryptographic primitives implemented in it, one of which is HMAC. The details of HMAC aren't important for this talk. It's enough to know that HMAC is an algorithm used for verifying data integrity, among other things. You use HMAC to generate a signature from a message, and use that signature later to verify that the message wasn't tampered with. Keysar's HMAC verification function looked something like this. The way this works is that the message is the raw unverified data, and maybe sig is the signature that someone provided. If you tamper with the message, you don't know how to generate the correct maybe sig, so you return false. But there's a timing attack here. If you can't see it, that's fine. I'm going to explain it right now. Here's what's going on. I've bolded the last line of the function because it's doing a regular string compare. We saw in the password example that string comparison is vulnerable to timing attacks. The comparison will stop at the first wrong character of maybe sig. A researcher named Nate Lawson noticed this in 2009 and verified that he could perceive the timing differences against the local server. The lesson here is that even though the HMAC algorithm is secure, its implementation ended up being not secure because of how the comparison was written. The fix, by the way, was to use a constant time compare function. They chose this one. It works fine. This got fixed in Keysar in 2009, but if Google could get this wrong in one of their cryptographic libraries, other people's code surely can as well. Mine can, maybe yours can. This is what makes timing attacks so fun, in my opinion. The mathematical part of the algorithm was all implemented perfectly correctly, but this library still ended up with a bug that completely nullified the security value of the math. This is one reason why people say you shouldn't build your own cryptography libraries, at least not unless you really decide to try hard and know exactly what you're doing at every step. The fact that the algorithms were implemented correctly, yet we could perceive some important facts about the system, makes this an example of a side channel. Timing attacks are a subset of side channel attacks, where the attack vector is based on how long the system takes to do something. There are endless examples of fun side channel attacks, but let's talk about one that's relevant to Python web applications. This attack caused websites that enabled gzip compression to reveal secret information to an attacker. Asheesh is going to tell you about that.
Thanks. So, gzip. In 2013, Django announced that you should disable gzip compression because it can lead to defeating Django's Crosssite request forgery protection, even if you use HTTPS. So gzip compression is cool. It makes web pages shorter. But apparently, gzip compression allows a third party to guess a user's secret value for the CSRF token. The problem was that you could discover secrets from the web page based on the length of the web page. If a person, that is, if the person serving the web page hadn't been careful. I'll explain the basics of cross-site request forgery, and then I'll show you how gzip and HTTP work together. After that, you'll see how the attack works. So cross-site request forgery is the idea that Django will give you a token that allows you to use a web form, like a login form, and have the server know it's really you using the form. I'll bring back Philip's nice form here. Oh, I won't, actually. Fully understanding cross-site request forgery isn't required for this section. What you need to keep in mind is that the server is sending a secret token, and an attacker wants to reveal that secret for this form. So Philip designed this form. I'm happy to bring it back. Django, the way that Django's cross-site request forgery works is that Django gives you a little secret token to verify that it's you doing the post request to the server to log in. And I'll add that as a hidden input here. So there's a random value here. The server had to send it to you, and it really wants to make sure no one else knows it. If someone else knows it, then the security protection goes away. Now, one of the best ways to protect information as it goes across the internet is HTTPS. So I've added a padlock here. HTTPS does a good job of making sure that no one on the internet can read the contents of that CSRF token, because no one can read any of the communication between the server and the client. One thing HTTPS does not protect, however, is the actual length of the HTML content. That's fine here, since all Django CSRF tokens are the same length. Now let's turn our eye toward gzip. Gzip's whole purpose is to make HTTP responses faster, smaller. That way, pages load faster. The way compression works, more or less, is that you take parts of the text that are similar, and you save space by saying them only once. I'm simplifying, but there you go. There's a lot of repetition in an HTML page. All those close tags add up. So here, compression identifies repeated text, and it can make the text shorter, compressing them into one. So that's what you need to know about gzip and CSRF to understand this attack. So let me show you how it works, step by step. Here, I put in a placeholder for the 9 characters of arbitrary text in an HTML document at the bottom. If the text there is similar enough to the CSRF token, then the document will compress shorter than if the text is totally unique. I'll pause here for a second to make sure that's all sunk in. If the attacker can get arbitrary text into a web page, and the web page uses gzip, and they can measure the length of that web page, they can figure out the CSRF token. You can measure the web page length if you're on the same Wi-Fi network as the target. But how do you end up with the ability to put arbitrary text into somebody else's website? One way to do that is the query string. A lot of websites have this feature where you can search for something, it shows up in the query string, and it gets echoed into the page. From here, the rest is history. In 2013, some researchers figured out how to build a working exploit that lets them mount an attack. They called it Breach, and they said it works in under 30 seconds with 95% accuracy for guessing a CSRF token of 32 hexadecimal characters. The reason they can do it is they're guessing one letter at a time. A useful side channel attack often has the property of letting you guess a complicated secret one component at a time. I'll bring back this exponential versus linear graph and let that sink in. So this is a graph, again, of how many guesses you need to guess the secret if you can guess one letter at a time, linear, versus having to try each possible value, exponential. This timing attack affected Python web applications in 2013, but this attack was one of a number of side-channel attacks that were ripping through web apps in the early 2000s. One of these involves an internal piece of the Python programming language called Python hashseed. Philip will tell you about that next.
So this attack was not a timing attack per se. It was more an attack on timing. Hope you'll permit the tangent. The idea is, if you know how Python's hash tables work, you can take a regular web application circa 2005 and slow it down to a crawl. This is because certain web applications were reliant on the hash table data type. Sadly, this picture is not the kind of hash I mean. If you want a delicious corned beef hash, there's a great restaurant down the street for that. I'm talking about the computer science term, which is what Python uses in its dict implementation. Anecdotally, hash functions and hash tables are named that way because you take something, chop it up, and move it around. Just like, for example, a delicious corned beef hash. Anyway, if you have a website that lets you search for things, you might have a URL that looks like this. If this site is written in Django, this set of query strings will get parsed into a dictionary like this. Dictionary is how Python spells hash table, which is a standard data structure in programming. Adding or accessing one key in a dict is supposed to be fast. In fact, that's the whole point of using a dict for this stuff, is that you can look up things super fast instead of having to iterate over all the keys to find the thing you want. If the data were stored in a list, you would have to iterate. Hash tables aren't made of magic, though, they're made of math. The point of the math is to put each dict key in a different place in memory based on a hash function. If you're ever unlucky enough to have two keys that want to be stored in the same place, then performance will degrade until it is as slow as a list. In 2003, some researchers named Dan Wallach and Scott Crosby showed that if you insert 90,000 items into a Perl hash table, it takes 2 seconds normally, but 6,506 seconds if you make all the items collide to the same hash value. We can use the same attack against something like Django. Parsing the query string data into the request.get object can be extremely slow if the query string is structured in such a way that all the keys generate collisions. The solution the Python team went with, which is what Dan Wallach and Scott Crosby suggested, is that instead of hashing the data we're given, we hash the data plus a random value, which is generated at Python process start time. If we do that, the attacker doesn't know what we're really hashing, so they can't choose values that all collide. This random value is the Python hash seed. As an appendix here, if you provide random data to the hash function, but you use a bad hash function, a researcher named Dan Bernstein will sit in his office and do some math, and then make a Python script that undoes all the security gains of the randomness. For a good time, read PEP 456 to see why the Python switched to a new hash function in Python 3.4. The demonstration code on the ziphash website is a really fun read. We've talked about a bunch of side channel and timing attacks. We've now primed your brains to understand and comprehend the most famous side channel attack of this year and possibly in the past decade, and Asheesh is going to tell you all about that.
It's true. So, by the way, I think I figured out what we should have called this talk. It should be type equals, press enter, what happens? So, but I'll tell you about Meltdown now. So Philip introduced this section as being about this famous timing attack. This is the logo for Meltdown, made by Natasha Eibel. Meltdown is a timing attack against Intel CPUs that was announced in January this year. Can I get a show of hands for how many people have heard of Meltdown? Yeah, OK, keep your hands up for a second. Come on, good. Keep your hands up now still if you understand Meltdown in depth. Yeah, all right, so like 6 people. So I'm hoping we can get at least twice that by the end of this talk. To do that, I'm going to explain enough computer architecture in 5 minutes so you can read the paper and understand the issue in its full depth. But I think in these 5 minutes, you'll get the solid gist of it. To get there, I'm going to explain a few concepts, starting with virtual memory. So here, I'm showing a grid of memory slots, starting at index 0, all the way up to 2 to the 64 minus 1 to be pedantic. It's 64 because I have a 64-bit operating system, and that's virtual memory. Virtual memory is accessed by number. That is, programs written in C can access memory locations by number. Another thing you need to know is that some of those ranges are reserved by the operating system kernel for its own data. So I've marked those in red here. Some areas are for the program. I've marked those in green. A program can access data by treating memory like a giant Python list and indexing into it with a number. So here's how a program might read data from a memory location it has access to. You can see we index into memory with a number. Main memory takes 100 nanoseconds to access, which is a long time for a computer. The CPU does 3 to 4 billion instructions per second. So 100 nanoseconds is actually quite a while. So there's another thing you need to know then, which is that the computer reorganizes memory so that memory accessed recently is faster to access. Here I have a program which accesses the same memory twice. The first time the program accesses this location, the computer has to fetch the data from memory, and it takes the full 100 nanoseconds. But the second time, it's much faster, probably 10 times faster, maybe even more than that. Next, here's a program trying to access memory it is not permitted to access. Memory 1 is marked as red on the diagram. The CPU raises an exception if the program tries to access it. Now, these data access permissions can change over time, and the CPU sometimes has to wait for the latest permissions information to become available. With Meltdown, our goal is to guess what's in memory 1. Our strategy is to have the CPU leave us a hint by how fast memory 10 is to access. We're not going to be able to read memory 1 directly, because the CPU will prevent it. But if we can get the CPU to leave us hints in timing, then we can get all the way there. And I'll show you some C pseudocode that achieves this. Oh, yes, timing. So here's some code. Before I go into it, let me say this is the most dense slide in the whole presentation, and this is the next 90 seconds in which you need to pay the most attention. So here's some code. It'll access memory 1, which we're not supposed to. You can see that memory 1 is marked red. Depending on the value in memory 1, we go and print out some values from areas of memory we are allowed to access. Now, the CPU is going to raise an exception, because we're not allowed to read memory 1. But the CPU doesn't know that yet, because the permissions are slow to access right now. even though the permissions are slow to access, the data happens to be fast. So the CPU does what's called speculative execution. It goes ahead and computes. It determines that, yes, data is an even number. And it does this load of memory 10. When the permissions finally arrive, the CPU raises an exception and undoes all the speculation. But there's one thing it did not undo. Memory 10 is now faster to access, because the CPU happened to read from it because memory 1 was an even number. The system state has changed based on the contents of memory 1, even though we aren't supposed to be able to access it at all. Now we can use the same techniques we described earlier in this talk to gain information step by step about the full contents of memory 1. And now you know enough about computer architecture to go read the Meltdown paper if you want. So Philip will take it from here.
So with this talk, we had 3 goals. We wanted to explain timing attacks in general. We wanted to talk about timing attacks in specific Python software. And then we wanted to broaden our horizons to kind of take that foundation and explain some famous and not so famous examples of side channel attacks in the wild. Hopefully everyone here has learned something today. Raise your hand if you learned something today. Yes. Great, fantastic. But we also know this is a very dense, very heavy talk. We are going to be out in the hallway afterwards, and we would love for you to come up and ask us questions about any of this, quite honestly. Or feel free to catch us. We're going to be here for the rest of the conference. And thank you all so much for coming. Like I said, my name is Philip James. This is Asheesh Laroia. You can find us at our Twitters there. I work for Patreon, who was very generous to send me here. And thanks again.
Thanks. And we really mean it about you asking us questions in the hallway track. So
Yes.
come meet us.